Hello, Chemistry 2330. This is continuation of Chapter 9, Benzene Derivatives, and this is Section 9-2, Reactions 1, or Reactions A. So let's talk about, now that we know that benzene is an aromatic system and it has different reactivity than other systems, let's talk about why that is and what reactions it actually does do. So the first thing we're going to talk about is what we call electrophilic aromatic substitution. So the reason we have aromatic substitution is that we have to have an electrophile attack the ring. And so up to now, we've been using nucleophiles to do the reaction. So in this case, technically, the benzene is the most electron-rich system here. So the benzene would be acting as the nucleophile because it's looking for the positive charge. But because we're actually doing the reaction on the benzene ring, we've turned it around the other way such that we have the positive charge is the thing that's interacting with the benzene first. And once it does, it kicks out a positive charge. So we start with a positive charge on our electrophile, and we end up kicking out a hydrogen plus as a leaving group, okay? So if we think about almost all of these mechanisms involve an attack by an electrophile to displace a hydrogen, and we generate H plus as our product for that. Okay, so let's think about this step by step, okay? So there's 3 steps in the mechanism of the electrophilic aromatic substitution. The first step is to the generation of the electrophile. Just in the case of with an SN1 reaction, we had to generate that carbocation. In this case, our first step is to generate our electrophile. Okay, so once we generate our electrophile, we can then have that electrophile react with 2 electrons in the double bond to create this new sigma bond between the electrophile and the benzene ring. When it does that, it generates a positive charge. Now, because that positive charge is in conjugation with 2 other double bonds, that positive charge can move around the ring by just flipping the electrons back and forth, back and forth. This makes that cation resonance stabilized because it can move all the way around that ring and be stabilized on a bunch of different carbons, making that first reaction be able to happen. Now, this is also our slow step, the attack by that electrophile to generate this initial sigma bond and form this delocalized cation, okay? So that means the next step is our fast step, where the fast step is where our proton leaves. Our proton is transferred. It's typically transferred to something in the reaction that'll act as a base. So in our case here, it's a Bronsted-Lowry base where we're trying to have it accept a proton. And then, so this is typically a fast reaction, which means we'll generate our product here, and we are going to re-aromatize our ring because the electrons that were on the nitrogen are going to come in down here and be a double bond, and the hydrogen is going to leave as a plus charge. Okay, so let's talk about that. And so if the first step in all of these reactions is generating the electrophile, that means we have to generate a positive charge somehow. And so if we looked at just trying to react chlorine itself with benzene ring, we have chlorine and a chlorine bond with all these electrons around it right here. Well, gosh, that's a non-polar bond. Where are we going to get our positive charge here? And we get our positive charge by reacting it with some Lewis acid catalyst or some other acid catalyst so that we can generate that positive charge. And so in this case here, we will always have, when we have these benzene reactions, we're going to have some catalyst here, and this catalyst is not consumed in the reaction, actually is used reversibly in the reaction to generate our substituted product, plus our acid is usually liberated from there. Okay. So we can do that with a number of different substrates. In this case, we're using the nitric acid and sulfuric acid as our catalyst to generate that nitro concept. All right, so let's look at this thing one step at a time. All right, one step at a time. So the first step in halogenation or bromination or chlorination is the actual breaking of this chlorine-chlorine bond. Okay, like I said before, it is a non-polar bond. And so to get a positive charge out of that, we're going to react it with this Lewis acid catalyst here. So the first thing that's going to happen is we're going to form this complex. So now we're starting to polarize. This is starting to become the negative side of the molecule, and this is starting to become the positive side of the molecule. And so if we think about it, this bond between the chlorines here has the electrons kick over to the last chlorine. So this half of the molecule is now negatively charged, and this half of the molecule is now our electrophile. Notice that it is a close contact ion pair, so they stabilize each other, and until that electrophile starts interacting with the benzene ring. So our next step happens to have the chloride, the electrophile, actually interact with the electrons in the double bond of the benzene ring. And so we form a new sigma bond with those electrons here and give us our cation from where the electrons were pulled away from this site here. Now this again is stabilized. It can move back and forth around that ring to help stabilize it and wait for the base to come in and interact with it. So the next thing that happens is, remember we had that close contact ion pair, and this was, oops, this was our negatively charged species here. This is now our base, and our base can come and interact with this hydrogen, kicking the electrons from that sigma bond back into the aromatic ring to give us our product here, plus to give us our HCl right here and regenerate our iron trichloride here. So notice this was regenerated in the system. We generated HCl, which can either leave as a gas or be dissolved in the solution, but we've regenerated our catalyst, and then this can go interact with chlorine again to continue the reaction to make more of the chlorinated product. Okay. So does this happen with other materials? Well, of course, we can do that with anything we can generate that cation on, or anything we have a partially positive charge on, we can do this with. So if we think about it, we can do this with sulfuric acid, where we're generating a positive charge on this sulfur. We can do it with a material of an alkyl halide, because remember, we can generate carbocations with alkyl halides as long as they're tertiary or secondary. And so we can get alkylation on the system. Or we already have a partially positive portion of this carbonyl. We can use that to act as our electrophile as well. And we'll go into each of those in detail in the next section.